Okay. Welcome to EE 123, Lecture 10. Woo! Okay. Today, Lecture 10, we're going to talk about the time-dependent Fourier transform. But before this, I want to go over a couple of things, and I just finished a couple of slides that I didn't finish from the last time, which will make me probably not finish a couple of slides from this time. We'll move to the next time. Till we cycle. It's going to be a cyclic thing, like the DFT. Okay. Midterm is Friday next week. It's open everything, so except computers. You know, no connection to the outside world through internet, ham radio, other devices. Nothing, no connection to the other world, external world, but you can bring whatever makes you feel more comfortable. My suggestion is to make a cheat sheet because there's just not going to be time, okay, to look at the book and so. But just in case, for the case it's like, oh, I didn't put in my cheat sheet and I can't remember what it. Then you can look at the book. Okay, so you can bring everything you want. No homework, solutions, notes, whatever you want, you can bring. Okay, but again, it doesn't help you, so don't bring them. But you could. Okay, so the other thing, who cannot stay till 5 p.m.? Can you come? Can you stop after the class and I want to chat with you? Okay, because we really want to give you this extra 1 hour time, but if it doesn't work, then for everybody, then we need to figure out what to do. Okay, how's the lab going? Who did not start the lab yet? So Frank had some suggestions of what to do with the lab. Some tips, and I put, he did 1, 2, and I put a tip 0, start early. Okay? That was tip 0. There's a midterm next week. You're going to be studying. Finish the lab. Okay? It is actually lots of fun, so start the lab. Okay? Who went to the lab ash yesterday? Using this extraordinary opportunity and extra time from us to help you. Okay, it's much extra time from us to go and adding a lab session, which is not part of the schedule, just for you to come and we can help you. So please use that as much as possible. Any questions? Yeah.
There aren't any plans on changing the lab time, right?
No, the exact lab time, no, but we might be able to schedule, there's one that's official in the lab, and there's one that we might be able to do at some other time, but it's difficult. Okay, so let me just pick up the previous notes. And I want to talk briefly about zero padding because this is a topic of many confusions, and part of it I could have seen in the homework. So for preparation for taking an endpoint DFT, remember the length of the DFT that we pick gives you the spectral resolution, which is 2 pi over n, okay, approximately. Okay, 2 pi frequencies divided by n number of bins. Okay, that will be the resolution of the spectral resolution. We may zero pad the window block of the signal to a block that's bigger than that. So zero padding, turns out, has no effect on the DTFT, okay, the discrete time Fourier transform, the continuous Fourier transform in that sense. So all the omegas doesn't have any effect. It has the effect on how the DFT is going to look like, but it has no effect on the DTFT. And remember, the DFT are samples of the DTFT, and when we zero pad, we just have better sampling. Okay, that's basically what it means. But it doesn't give us better resolution. What it gives us is better sampling of the DTFT for visualization purposes. Okay, so if we take an n-point DFT of a zero-padded signal to obtain the block of n spectral samples. Okay? So that's what we're going to do. And so now the question is, let's consider the DTFT of the zero-padded sequence. Okay? Since the zero-padded sequence is of length n, okay, no matter where it's zero-padded or not, it's still of length n. So its DTFT is not going to change. Okay, if I have a sequence of size n, and I zero-pad it by 3 times, its DTFT is not going to change because I'm still going to sum from minus infinity to infinity, and it's non-zero between 0 and n minus 1. That's it. So it's not going to change that sum. So the fact that I zero-padded the sequence doesn't give me more information when computing the DTFT. What it does, though, is slightly different for the DFT, because what the DFT does is evaluates samples on the DTFT. So if I look at the endpoint DFT, okay, the endpoint DFT, if I write them down, I can quickly show that this is in fact the same as E minus J 2 pi over n times nk. And that corresponds to the evaluation of the discrete time for a transform at omega equals k2 pi over n, which is exactly what we have here, those values. Okay, so I'm computing the sum for those particular frequencies. And those particular frequencies correspond to omega equals k2 pi over n. Okay, that's exactly what is going on. Okay, so if you want more samples closely spaced by approximating the DTFT, so sampling it better, you just zero-pad. And you can take it to the extreme, zero-pad to infinity, and then the DFT becomes the DTFT. Okay? All right, any questions about that one? Because this is a really important point. Okay? So it doesn't add you information, it just beautifies it. Okay? Now, the other thing is that the ordering of the DFT are unusual, and that is also a source of confusion. The DFT assumes that n equals 0, the signal of n equals 0 is in the beginning. It also assumes that the k equals 0, or the DC, or the 0 frequency, is also in the beginning. When we look at signals, normally we look at 0 in the middle, right? Because minus infinity, plus infinity, 0 in the middle. Okay? When we look at frequencies, we look at minus pi to pi and 0 in the middle. And this is not the case for the DFT. Okay? People have chosen it to be starting from 0 to n. So that's a little bit different. And so what happens is that the positive frequencies of the DFT are in fact the first n over 2 samples. And the negative in the second half correspond to the negative frequencies. Okay? Right, so the second half corresponds to the negative frequency. In order to display nicely, what we do is we compute the DFT and then do FFT shifts, which basically takes the last n over 2 and then flips it, and basically puts the negative frequency in the right place for visualization. One of the reasons that they did this is because often for real signals, we're only interested in half of the spectrum anyway. So just by doing this, then you can just, you compute the DFT and just display the first half. And that's enough. You don't need to display the second half. And that's why originally it was done. Okay. So if this is my sequence, and I had these frequencies, that is the positive frequencies. These are the corresponding to the negative frequencies. Okay? So this corresponds from 0 to pi, and this is from minus pi to 0, or from pi to 2 pi. It's exactly the same. Okay? Because it's periodic. Okay? And these are samples of the DTFT, which is dashed. If I zero-pad my sequence, so I zero-pad here, then this is n equals 0, and I zero-pad over here. Now I get finer sampling of the DTFT. Okay, so just finer. All right? I showed you this last time, that the fact that I zero-pad doesn't add information, and that is really visually striking. And then I showed you an example of this. So just to summarize, length of the window that you have determines the spectral resolution. As I get more and more samples out of my signal, I can resolve the frequencies better, as long as they're stationary. Okay. Type of the window determines the side lobe amplitude. Some windows has better trade-off between. Some are optimal, Kaiser window, Dolph window, with different optimality criteria. Okay. Zero padding approximates the DTFT better, but it doesn't introduce new information. It's just an interpolation that doesn't give you new information. So here are kind of problems and solutions. I don't want to spend too much time onto this, but I put them in the slides. It's really nice for basically debugging. But if you don't have enough frequency resolution, you need to increase L, okay, the size of the window, to get better frequency resolution. At the trade-off of time resolution if the signal is not stationary. Okay, if it changes over time like most signals do. Okay. Spectral errors from leakage, you can use windows that have better side lobes or, again, a bigger L. Okay. And so on and so forth. Okay. So, yeah, FFT shift. FFT shift, all it takes the last part of the DTFT, the DFT, and then shifts it. There's no indexes. It's just vectors, right? It's just there's no indexing there. It's just it takes the last part of the vector and puts it in the beginning. That would correspond then to negative frequencies and positive frequencies. Was there a question here? Okay, so I want to show you some of the subtleties, and this came out from discussion today in office hours about one of the questions that you had in the homework. That was the overlap and save method that you want to do processing using the DFT, filtering in the DFT as opposed to using filtering as opposed to doing convolution. Okay, so you want to do this in the DFT directly. So in the homework, one of the homework the question is okay, I want to low pass filter a signal. What I'm going to do is I'm going to take this window. I'm going to compute its DFT. I'm going to then multiply by this mask. And then I'm going to compute so this is a circular convolution, and I'm going to take the last sample, which is the valid linear convolution, and then I'm going to store that one. So effectively, what I'm doing is I'm convolving with an impulse response that is the inverse DFT of that. So this it kind of makes sense, right? It's a low-pass filter, sure. Yeah, it is a low-pass filter. It has for frequencies correspond to 0 to some, pi over, I don't know, 6 maybe. It passes the frequencies. The rest, it makes them 0. And then from the negative frequencies, again, it passes them. Right? That's great. So, yay. Right? First of all, one of the questions there, did I implement an ideal low-pass filter? Because this looks like an ideal, right? I'm like taking correct, right? Of course, it doesn't make sense because ideal low-pass filter is an infinite impulse response, and this one doesn't have. So what the heck am I filtering with, right? So what is the impulse response of this filter? Right, you take the inverse DFT, because that's the way you process things, right? In this particular way, you take the inverse DFT, and this is what you get. Okay, so it's kind of like a sampled periodic sink, and because this is real, right? And the fact that if it's real, then everything needs to be around 0, so the main peak should be around 0. But because, unfortunately, things become periodic, then I got the other part in the other side. And as it turns out, this is the impulse response you are convolving with. Now the question is this the right low-pass filter that I'm interested in? So what is the DTFT of this impulse response? Is it something that looks like this, like a square? Do you want to see it? It's crazy. I'm going to compute the DTFT of it, okay? This is the DTFT of it. Wait a second. This is the DTFT. This is zero frequency. It is kind of a low-pass filter. Not the best one, though. Okay. Now, mind you, that for the frequencies corresponding to those values of h of k, it is on. Okay? So there are places here which is 1, it's 1, it's 1, it's 1, it's 1, it's 1, it's 1. It is 1 over there. But in between, it's not 1. It is 0, 0, 0, 0, 0, 0, 0, 0 in discrete places, but not in between. Okay? So, one of the things that you need to understand is that you cannot do a zero delay filter that has a really nice frequency response, because this is in fact a zero delay filter because it's mostly concentrated here, although it leaked over here, really far away. But the idea was here because this is real, it shouldn't have any delay. If you had a pure low pass filter, right, it should concentrate around 0 and it would have no delay, right? But now that's a problem. If I had a linear phase multiplying this, that would shift the impulse response such that it's centered around the middle. And as it turns out, if I would have done that, then I would have actually got a decent low-pass filter with the DFT too. Because then that part would not alias. I would kind of circularly move it to the center, and then everything will taper off. So the DTFT would have looked much nicer. So you got to be careful when you deal with processing of discrete time signals, because you can make mistakes like this. Okay? You can make mistakes like this. So if I would have added a delay to that filter by modulating the frequency response at the DFT samples, then that would shift to the middle, and then the DTFT of that would have been a much nicer, smoother looking low-pass filter, yes.
Would it be smoother because H of n is not periodic, or is it periodic?
H of n should not be periodic, but if it was centered, then it would have been a smooth type of a function that decays at the end, which doesn't have large variations, right? So the DTFT of it would have been more closer to that, right? As opposed to here, I evaluate those at the right places, but in between it goes crazy. It goes crazy because of this huge discontinuity. Okay? So you got to be careful, okay? And that's the idea. Just be careful. Okay? Understand what you're doing. And this is one of the things. Okay? And this is why you're taking this class. Because otherwise, it's like, oh yeah, why not? Just do this. Right? I mean, this would be a trivial thing that somebody would do, right? Why not? Like, compute it and then do that, right? Slow pass filter. But the result will be not good. Okay? All right. Let's move on. You know this one? It's a cake CD. Shh. This is my joke, so don't ruin it. It's what? It's who? Which one? Yeah, but I have a joke on top of that. So this is, I don't know, some people find it funny, but some people don't find it funny. Like I have a colleague at the end of the corridor, Laura Waller. She didn't find it funny. So then I asked her, "Hey, Laura, how do you know this guy's insane?" What? Yeah. Why? right? So the Fourier transform of the cat is not symmetric, so the cat must have an imaginary component. Hence, this guy is... And she found that funny. What a nice colleague. Okay? So spectrum's not symmetric, cats must be imaginary. Great. Okay, last time. Frequency analysis with DFT, also today a little bit. Window and zero padding. Today, we're going to talk about time-dependent Fourier transform. When things, the assumption of things that are stationary is not longer, and we're interested in seeing the dynamics as well, how frequency change. And that's very important, especially when I look at a radio signal, but and other signals as well. Okay? And so I'll give you some explanation. But again, we need to understand, what does it mean? What are the variables? What are the parameters? How do we actually determine what is the actual resolution that we have, both in time and frequency, and what are the trade-offs? Okay. So one thing about this, that the DFT that we learned is really one out of a large class of transformations that these are tools. These are like, people have tools, like hardware people that have all these tools, and they pick up, it's like I have a screwdriver, and it's like drill, and I can solder, and I have all this like really cool tools. The tools that we have in DSP are basically, a lot of them are transformations, for example. Okay? Transformation, DFT as a tool to understand the frequency domain, right? But there's huge class of them. They're used for analysis, they're used for compression, they're used for denoising, detection, recognition, approximation. Okay? If you want to approximate a signal, you can compute some operation, a transformation on it that maybe will move. It will be like a vacuum cleaner, like a broom that moves energy, from like spreads out, like moves it to like a few spots, okay? And all the noise stays everywhere, and so you take the spots, lift them above, and then wash the floor, okay, and clean them, okay? So one of them, for example, sparse approximation is really one of the hot topic in signal processing in the last 15 years, okay? And how to represent things in a sparse way. And so taking a transformation that exploits some structure in a particular type of set of signals, once you use these sparse transformation, then your signal that could be spread out everywhere in the time and space, it moves it into just a few number of coefficients. Here's an example. Let's say I have a sinusoid, and that sinusoid is buried in noise. I'll do my DFT magic on it. Noise, what will happen to noise after you do DFT? It's an orthogonal transform. Noise in one domain will become noise in the other domain, spread out. What would happen to my beautiful sinusoid? Will rise from the ashes above the noise, and I'll be able to detect it. That's because it's sparse. There's only one component there, right? If it wasn't sparse, if it was a whole spectrum, then it's kind of hard to say, it's like it's going to be buried here and it's going to be buried here. But if it was just, a few coefficients, that will be easy to separate. Okay? Then you can think about, how can I denoise? You kind of grab it by the neck, clean the rest of the stuff, put it back, do an inverse Fourier transform, and you got yourself a denoise signal. Okay? So here's an example. So, what we're going to talk about today is another type of transformation that take time into account, and that is going to lead us eventually to a wavelet type of decomposition. But we'll get there not today. Okay? So, yes, here's an example of something that we'd like to do a spectral analysis. This is a spectrum of a bird chirping. Okay? So this is the time signal, and this is the spectrum. So it's interesting, right? You look, there's a time signal. You look at it, it's like, it's not homogeneous. There happens something there, and that's the spectrum. And if I show you the spectrum and I ask you spectrum of what it is, this, it looks like speech. Is it a bird chirping? Is it something else? It tells you some information, but it doesn't tell you the whole story. The whole story is that when a bird chirps, things change over time. Frequencies change over time, and now I see something constant. Okay? There's really no temporal information here that I can use. So if I wanted, for example, to classify bird chirping from people speaking, I would find it hard to do using just a spectral analysis. I compute a spectrum of one, I compute a spectrum of the other. Well, they look the same. I guess it's the same signal, right? So then birds and people would not be able to. Okay. But obviously there's something different. Right? So we need to find what's different. So there's no temporal information here. Was it? Did I? I think I was supposed to actually play you this. Obviously, it's quite a complex signal. Do you hear this? You want to get? I don't think this dynamics is expressed in this spectrum. Right? It's quite a complex signal. So we'd like to see, things have changed. Well, what changed? Actually, kind of the pitch changed, the frequency changed, right? Over time. We want to be able to see this. So how do we do this? So here comes the time-dependent Fourier transform. What we're going to do is we effectively going to break the signal into blocks. Okay? We're going to break the signal into blocks and compute a windowed DTFT for every block. Okay? How do we write it down? Okay? We write it down this way. Now, here's an interesting mapping here, right? If you think about it, we started with a small x that has a parameter n, right? It's just a time series. And often when you do a DTFT, you get omega, right? You map one parameter to one parameter. Okay? N is mapped onto W. Now we get a two-dimensional space. We get a result which depends on n. N depends on omega. And here's what it basically says. Okay? I'm going to take my signal, multiply it with some window that is finite, and I'm going to compute the DTFT. So just imagine m equals 0, okay? M equals 0. M equals 0 means that I have x of n, the usual one, multiplied by a window that is about 0. And I'm going to integrate over all the m's. Okay? So then what I'm going to do is I'm going to move over all these m's and then compute for every m we're going to integrate over m's. Okay? And so for every particular n, we're going to integrate over all those shifted versions of our signal. So it's a mapping for one to do. I'll show you an example. Okay? But basically what it does is simply slide a window and you compute a DTFT. So here's the thing. Here's the example. So what you do is you take your signal, you multiply it by a window, okay, and compute a DTFT. And then you slide your signal, you multiply by a window, and then compute the DTFT. And then you slide your signal, multiply by a window, and then compute the DTFT. So for every small n, you get a whole shifted version of the DTFT. Yeah.
So do these windows overlap?
In this case, they do overlap, right? Because now we're just counting by ones, so they do overlap. Okay. So this is why it becomes a mapping of n and w. Okay. And it is. So this is also called the short time Fourier transform, time-dependent Fourier transform, shift time Fourier transform, all those versions of something with time and Fourier transform and shift. Independent. Pick your favorite one. Okay? So then I just multiply, compute. So if you think about it, if I wanted to compute this, pretty computationally intensive, right? for every shift I need to compute the DTFT, but who cares? We're now trying to do some certain analysis, right? Okay? So, yeah.
Was the window the same size for all values then?
Yes. Yeah, it's the same window. It's the same window. We'll get to that, though. That's an interesting concept. What if the window size was not different? It makes it hard to analyze. But okay, so here's our chirp signals. Here's actually the time-dependent Fourier transform. This is the frequency axis. And yeah, I computed the DTFT. I'm supposed to get 0 to pi, but I know the sampling frequency that I calculated, so that pi then corresponds to a particular frequency. Okay? So I just plotted just so you see what they actually are. And this is over time. Look at this, beautiful. First of all, it tells me that at this particular time point, I would have this particular spectra. And at this time point, I have a different spectra. Okay? So now I got more information about my signal. If I would speak and try to then classify a speech signal using this transform compared to this bird chirping, it will be very different, right? So you can think about transformations that would make your signals different in a certain space or make them close. Okay? But the time-dependent Fourier transform will separate that. Yes?
When we define the window at the end, is n always at the middle of the window, or is it dependent on how we choose whatever window?
So the windows we talked about before, it's the same windows that we did all this analysis on them. We assume that they're real and symmetric. Right? We assume that these windows are real and symmetric, and they're about 0. Right? So the windows are about 0, either rectangular, triangular, Hamming, Hanning, Kaiser, Bessel, pick your favorite. Gaussian. Well, now I have to go through this again, but it was so pretty, so I'll go through it anyway. Oh, it's lovely. Okay, so I get different spectrums for different time. That's great. Okay? Computationally, I want to compute that, though, right? And obviously, because I showed you spectrograms or waterfall type of diagrams, this is a waterfall type diagram in some sense. You can compute them, and you can compute them on a computer. And anybody has an idea of how to compute them on a computer? Using the FFT, right? So we need a discrete version of this, right? Discrete version of the whole thing. If the DFT was a discrete version of the DTFT, okay, it evaluates the DTFT on discrete points. We want to do the same thing in this case. Okay? So now we're going to define a discrete time-dependent Fourier transform. We're going to call it x sub r of k. Okay? R is where we're going to be. It's the time dimension or the sample dimension. K would be the frequency dimension. But now they're all indexed. Everything is like 1, 2, 3, 4, 5, 0. No 2 pi's, no things like that, right? And we're going to define it that way. We're still going to sum over m, but now because we're looking at a finite size, right? Our window is of size L. Okay, so we're just going to sum from 0 to L minus 1. And then, so this part is the typical windowed DTFT, right? This is the typical. This part is slightly different because it depends on R and capital R. Okay, so L is the window length, the usual, right? How big the window. N is the DFT length. And the DFT length could be bigger than the window. That means I'm zero padding. Okay? Okay? Does this make sense? It's like zero padding. And then R is the jump of samples. Capital R. So if r equals 1, I'm shifting 1 by 1 samples. Okay? If r equals 1, I'm just shifting my signal by 1 sample like before. But now I can also define a capital R, which makes me jump. And if I define R to be the size of the window, L, then I have no overlap. Okay? So I can control that. I can do half overlap, more overlap, less overlap, skip, and so on and so forth. Okay? Yeah.
Previous aside that y-axis was window length, we had 0 to 12 previous aside. The y-axis.
The y-axis,
Yeah.
this is amplitude. I'm showing the intensity of the pixels. So the other thing is, how do you display this? The way I'm displaying this, I'm displaying as the image, where the value is the intensity of that pixel. That is a good point. Thank you for that. Okay, so when I look at the cross-section here, I'm plotting the intensity. Okay, this is one way to visualize this. I can visualize it in color. I can visualize it as a 3D surface. There's other ways to visualize this. The majority of way to visualize it is an image, that the value of the function looks like an intensity, where white is usually high and black is low, but it could be inverted. Does this make sense? It's a two-dimensional function. Right? The result is a two-dimensional function. I need to display a two-dimensional function. Stop. Okay? I need to display in one way two-dimensional functions as an image. It's one way. Thanks for that. Okay, so now there's obviously a trade-off here between time and frequency resolution. Okay, because I'm going to pick a certain size of a window, and I'm going to be computing the DFT on, or the DFT on. This is in fact a DFT for different type of, or a zero-padded DFT on different parts, and I'm going to compute it using the FFT, of course. But there's definitely a trade-off here. What is the time resolution, and what is the frequency resolution that I have? So the next topic I want to talk about are Eisenberg boxes. That's also a major source of confusion. But here's the concept. The concept is that we have a box that defines uncertainty. And the area of the box is constant. I can stretch it one way, then it's going to be narrower in that one dimension. I'm going to squeeze it in one way, it's going to go that way. So it's kind of like this incompressible fluid that I'm just going to press on one side and it's going to spread to the other, and so on and so forth. But it has a certain area, and there's no way for me to get it smaller than a particular area. So, Eisenberg boxes. This is really, time frequency uncertainty principles, the Eisenberg uncertainty principle. It's like you cannot detect. It comes out everywhere. Like particular quantum mechanics. You cannot determine the wavelength, like where a particle is, and know exactly what its momentum. All this stuff comes down to the same thing. Okay, and what it tells you basically is that if you look at Gaussians, and Gaussians have parameter, which is the standard deviation. Standard deviation in time, multiplied by the standard deviation in frequency, is always bigger than half. Beautiful. Okay? Always bigger than half. For Gaussian, it is exactly a half. Other signals, it's bigger than a half. Okay? That's what it tells you. So, if I want to be able to localize my signal in time, I'm going to look closer. I'm going to take a window that's narrow in time. But because of this, what will happen is that, it will become narrow here, so it's going to spread here. Okay? So I'm going to have more uncertainty in the other dimension. Okay? Now let's translate it to the discrete case and look at the DFT coefficients. Okay? What does that mean? And where's the uncertainty kind of plays there? And this is an analogy, okay? you can fight with me on the right coefficients, but this is an analogy. Same thing. So DFT have coefficients, right? I have x of n and I transfer to capital X of k. So if you think about this, if this goes from 0 to omega, to 0 to pi, okay, or in fact from minus pi to pi, okay, so I have a range of 2 pi frequencies. For this range of 2 pi frequencies, I have n samples. So each DFT coefficient represents a certain delta omega. It also represents a certain delta t. What is delta t? It's the size of the window that I picked. Okay? I picked n samples. Okay? What is the spectral resolution? It's 2 pi over the number of samples. So, delta omega times delta t equals 2 pi all the time. Okay? So if I'm going to take a smaller window, I'm going to have more uncertainty in time. If I'm going to pick a larger window, I'm going to have more uncertainty, the opposite. Smaller window, better uncertainty in time, worse uncertainty in frequency, and the opposite. Okay? So in this case, I break the plane of time and frequency into these type of boxes. That's how. This is the DFT. This is really the Eisenberg boxes of the DFT transform. Okay? Uncertainty of length n or L, whatever window I pick, and certain uncertainty in omega. Okay? And this one DFT coefficient will have basically this uncertainty box. Okay? My signal somewhere is around here. Okay? My information. And that's an uncertainty. I give you a coefficient, you know that it's spread over time that much, it's spread over frequency that much. Okay? Does this make sense? So actually, here's the question. What is the effect of zero padding? Ooh. It's a tough one. What is the effect of zero padding? What did we say when you zero pad? It doesn't change. Right? There's no information, so it doesn't decrease the uncertainty. What does it do? What's it do? No, random. There's nothing random about that. So each coefficient in a zero-padded DFT is going to have a box. Where are these boxes going to be? Let me argue it's going to overlap between these. I'm going to have finer sampling, but each one of the DFT coefficients is still going to have this uncertainty. Okay? So in fact, it's like adding more boxes in between, but the boxes have the same size. So each coefficient here, I have a coefficient in between, but it still have that kind of an uncertainty. It didn't improve the uncertainty. Okay? It's just basically overlapping blocks. Okay? If it was smaller, then I would decrease my uncertainty. But they're not the same size, yes.
Can you get any other information out of having those two?
No. There's really not, it tells me everything. Except if I do nonlinear processing, maybe something. Actually, no, it doesn't give you. It actually doesn't give you. Because the space is just defined by what you just, by what you just have. Zero padding doesn't really give you anything. Zero padding just doesn't give you everything. Okay. So it is just overlap tiling of that time frequency space. Yeah, quick.
Is delta omega delta t the thing that's not supposed to be less than half?
For the discrete case, for the discrete complete, it's always 2 pi.
Is it like the relevant quantity though?
If you decrease that, that will increase. If you increase that, that increases. It's 2 pi. So here's the frequency tiling, time frequency tiling of the short time Fourier transform, or the discrete time, whatever I mentioned before. Okay? So now I take smaller windows, and in the case where I don't take overlapping windows, there's non-overlapping windows, each one of the coefficients for a particular r and a particular k would have some time resolution and some frequency resolution. So it's basically breaking, if the DFT was just breaking into block on top of each other with no time resolution, now because I broke it into smaller parts, it's basically breaking into this kind of grid, but again, the area of each one of them is going to be the same. Okay, so I traded off the spectral resolution with better temporal resolution. Okay, that's exactly what I did. And what is the effect of R on tiling? What's the effect of R? R would be overlapping or non-overlapping. So let's say R is now 1 or 2, or let's say half the window. Then I get overlapping in time. Okay, but the size of them is the same. It's just an interpolation, but the size, the uncertainty is the same. Okay, so tiling will be overlapping blocks. What if I increase n? So increasing n is 0 padding. It's more overlapping in this dimension, but again, not improving. The last couple of minutes, what I want to go is some applications. There's an orca whale, and the question is, so this is what a spectrogram. These are called spectrogram, by the way. Whatever the time frequency type of analysis, they're called spectrograms. And this one is, you see how much structure and information you can actually get from this time frequency decomposition? So much more than just looking at the frequency. So here's, what's the difference between these two spectrograms? And this definitely can appear, let's say, on a midterm or something. Especially if it's shortened, there's not a lot of time, so you just put a picture. Yep. There's no noise here. Spectral leakage because of the window. Yeah. Anyway, the window type is different. So in one case is we use this rectangular window. So you got, whenever you have a sharp edge, then it kind of like there's lots of side lobes, and this one used a different window. Okay. So the case here was one of them was Hamming and one of them were rectangular. So you got all the spectral leakage when you have like really sharp changes in the sound. Okay. What's the difference between these two spectrograms? It's an obvious difference, right? The what? The window size of B. What would bigger mean? Better resolution in? And smaller? Better resolution in time, right? So here we have better resolution in frequency. So this one is bigger. But we lose some resolution in time, and there's some variation here that we can kind of detect very nicely. Here it's kind of hard. Okay. Here we can see changes over time, which here is kind of they're blurred out. Okay. Yeah, this one is a shorter window. Look at this. Okay. So this one's shorter window, bigger window. Okay. So this is the case where you've got a bigger window, then you have narrower resolution and frequency. Okay, so my resolution and frequency is better. Here's an example of a spectrogram of FM radio. You know what? I'll explain this actually next time because we're running out of time. One of the cool things, by the way, that we could do with SDR is look at the spectrum of FM radio, and for example, 94.1 KPFA. Turns out this would be the left plus R channel. This is some pilot. This is the stereo channel. This is a digital information it gives you about the station, but there's other 2 stations on top of it that you don't hear unless you have a really good radio or the SDR. One of them is French Haitian, and one of them is Punjabi radio, and one of the labs will be to decode those. So. All right. So thank you very much. Have a nice weekend, and study well. Work on the lab, and I'll see you next week. Monday, no lecture. No lecture Monday. Tuesday, ham radio lecture in the evening still.